So till now we have covered first two chapters, introduction to threads and thread control, like sleeping, joining, interrupting, okay, creating threads, threads lifecycle. This time we will start synchronization. And in this one we will see race conditions, synchronized keyword, synchronized method, synchronized block, okay, and reentrant locking, basically, not reentrant lock. We'll see that one in advanced synchronization. So we can start our chapter 3, synchronization basics. When multiple threads access same shared data, then we get corrupted data in the output. Okay. So one thread reads a value while another modifies it. Our updates get lost. And we call that one race condition. We have seen this one in our first chapter, okay, in introduction to threads. And the fundamental problem that synchronization solves here is race condition. The shared memory problem. So let's say we have this code here. Threads within the same process share the heap. We know that they can all access the same objects. Okay. This shared access is both powerful and dangerous. So let's say we have this class counter, and inside that we have one field count, and we have one method increment, and in this one we are increasing this value. So we have one problem with this code, and that is when we will work like this counters instance with multiple threads, then we will get a wrong output, okay, like not expected one. What could go wrong? The innocent looking count plus plus is actually three operations. Read the current value of count, then add 1 to that value, write that result back to count. So if two threads execute this simultaneously, their operations can interleave in unexpected ways. Okay. So maybe we can see this one. Okay, we can keep this one for now. We can see some things here. What we can create is this one, int count equals to 0. Okay, so we are getting one suggestion for synchronized. Let's not do that one. Increment this one plus plus, and now we can get this one. Okay, and right here we can create two threads, or maybe we can create one like runnable interface that will be as equals to this. Let's not go that much. Now we can create thread 1, thread 2, start this one. Okay, right, and we can comment out this one for now. And if we will run this one, then you can see we got 1652, right? So not 2000. And if we rerun this one, this time we got, okay, close to 2000. If we rerun this one, okay, same value. Rerun this one. So you can see 1885. So we call this one race condition. So let's understand this one more closely. Okay. So why this interleaving happens? So our CPU doesn't directly work with the main memory because it's too slow, and our each core has its own cache. Okay. So that is very small but ultra fast copy of our memory. So when this thread 1 on, let's say, core 1 reads this count, okay, it copies the value into core 1's cache, okay, and then thread 2, let's say on core 2, copies it into core 2's cache. So each core operates on its own copy, and there's no guarantee about when those caches synchronize with main memory. Okay, so we call this one our Java's memory model problem. And without explicit synchronization, those threads might see stale data. So our race condition is just one bug. Okay. Understanding race conditions. Race condition occurs when the correctness of a program depends on the relative timing of multiple threads. The outcome is non-deterministic. It varies between runs. Okay. Thread A reads this one, thread B reads this one, A writes this one, B writes this one. Lost update. Demonstrating the problem, you can see here, we will get different outputs if we run this one with 10K. Okay. This is called a data race. Multiple threads accessing the same variable where at least one access is a write without proper synchronization. Now, critical sections. Critical section is a piece of code that accesses shared data and must not be executed by more than one thread at a time. So in our counter example above, the count plus plus line is the critical section. Okay, this one. This one is our critical section. Okay, this line. The goal of synchronization is to ensure mutual exclusion. Only one thread can be inside the critical section at any moment. The mechanism Java uses to ensure this we call like lock or monitor. When we say code is thread safe, we mean it behaves correctly even when multiple threads access it concurrently. So we can also think like some real example, or we can compare. You can think of this one like a bathroom. Okay, when we go in and we lock the door, so nobody else can enter until we come out and unlock that one. Same thing here. So when we are in, others have to wait. And Java provides this one through locks. Every object in Java has a built-in lock. Okay, we call that one intrinsic lock or monitor. Okay, so these two are the same thing: lock, intrinsic lock, monitor. So our thread acquires that lock and does its work and then unlock that one. Okay, or release that lock. Now, how we can work with those intrinsic locks? So we can work with those with synchronized keyword. Java provides this one to create critical sections. Every object in Java has an intrinsic lock called an monitor. A thread must acquire this lock before entering a synchronized block and releases it upon exit. Synchronized method, let's see. So public counter. So we just have to write here synchronized keyword. Okay, void increment and also in get count synchronized. Now you might wonder that why we need synchronized here, like in get count, okay? Because it doesn't modify anything, right? So we have here some reasons. First one is memory visibility. So without synchronization or without the synchronized keyword, our thread might see or might not see the latest value, okay, of our count variable, because it might see like stale cached value. Second, atomicity of reads. Maybe on some hardware, reading like 164-bit long or double is not atomic. Our int is like 32-bit, but our long and double are 64-bit, right? So maybe some hardware read those like in two parts, like 32-bit and 32-bit. So maybe one thread could read the first half before an update and the second half form after, right? So we must use this one, synchronized. All access to shared mutable state, like here count, must also be synchronized. Okay, so both reads and writes. When a thread calls this one, it acquires the lock on this. We will see. Okay, so in normal method, like synchronized methods, we acquire this lock. This like represent the instance of this class we are calling. So the counter instance executes the method body, releases the lock, even if an exception occurs. Other threads trying to call any synchronized method on the same object must wait. So we mentioned here synchronized method, not static synchronized method. And we have some differences between these two, like normal synchronized methods and static synchronized methods, because they acquire different locks. Okay, so other threads, those want to do something not with this method, even if we have like another method with like normal method with synchronized keyword, they must wait. Okay, now first thing, synchronized methods. Making a thread as synchronized means the thread must hold the object's lock for the entire method execution. Instance methods lock on this. So let's say here we have one class, bank account, double balance, and we have here this method deposit synchronized. Okay, we can add this one, withdraw, we can withdraw this one, and also for reading purpose we synchronize this. So all three methods share the same lock. if thread A is executing deposit, okay, thread B cannot execute withdraw or get balance until A finishes. This is the one thing with like normal synchronized methods. Now let's see static methods. Static methods lock on the class object. So let's understand this one. So right now what we can do, maybe we can see in this one, or that doesn't matter. We can remove this one for now, or maybe we can keep this one. So here we have two classes, data processor and counter, right? Now when our JVM loads these classes, it will create a new class loader, right? And load the classes from the from the new class loader. Okay, so this one is not relevant. So when our JVM loads these two classes like counter and data processor, or basically loads our class bytecode into our memory, our JVM automatically creates one single companion object on the heap to store these classes blueprint, right? So we store these classes blueprint in one object, and our JVM create only one that kind of object for one class. So our JVM create one single object for this one and for this one, and we will see in reflection as well. Like this will also help our JVM to like do some other things as well. We'll see. And if you want to see that, we can use our java.lang.class. Okay. So maybe we can see like we can create object O equals to, let's say, data processor dot class. Okay. We can do that. But now, as you know, in left side, we are putting reference to object, and we cannot create here, or we cannot call O dot anything. Get class we can call any method basically, or maybe we can see here with counter. Okay, can we call this one? No, we cannot do that. So if we have to do that, then O.count, either we can create here new instance, but this one is again deprecated, and here we have to put its reference. Okay. So unhandled exceptions, illegal access exception, and instantiation exception, we can do that. Okay. And this one is deprecated. We usually don't use this one. So now we can run this one. Okay. And maybe we can just comment this thing. So we got 0 here. And we have some other method as well that we can do here something like this, counter equals something like that. And now we don't have this one. Okay. So we can rename this one to reference. Okay. So we can also see that. So we got class counter here. Now, what information does it contain? It is a regular Java object, right? So we can invoke methods here in this one to inspect the structure of this class. And we will see that one in our reflection. So we can access metadata like class name, package name, modifiers, and also superclasses as well. We can also access structural arrays. We can also access here some other things like structural arrays, lists of all methods, fields, and constructor objects defined inside this class. We can also inspect any runtime annotations we apply to this class. Okay. The main thing is our JVM only loads one class definition per class loader. Okay. And now we can understand our static methods synchronization. Static methods lock on the class object, and we know that that will be only one per class. So if we have multiple instances, right? If we have multiple instances of like our counter class, counter O equals to this one, counter O2 equals to this one, okay. And if we have here static method, like synchronized static method, so we have to make static for that. Now, if we have one static method here, we can create one. So, or maybe we can see different, right? Static int count2 equals to this one. Now what we can do, we can create here one method basically that will be static void. We can do that one. Okay. In never use, that's fine. And if we put here synchronized, so right now, when we call this method, then that thread will acquire its class definitions object lock. Okay. Not any instance lock. All right. So two threads cannot acquire that lock as well because we only have one, and any thread can only acquire one lock. So this is the difference. Now we can see synchronized blocks. Sometimes synchronizing an entire method is not very a good practice. Synchronized blocks let us protect only the critical section, holding the lock for less time. So instead of synchronizing this method, we can synchronize any particular block. Okay, so if we are synchronizing this block, then definitely we need one lock, right? Any object lock. So we can create here new object, dedicated lock object for this block only, and then we can acquire its lock. And now if we have another block that is not relatable to like this work, then we can create one new object for that block as well. Okay, for different block. So we can create multiple objects here, and we can work like concurrently with unrelated data. Okay, so this is one practice we can see or we can do. So we can copy this one. We can come here and we can do that. Okay, remove public here, and we can create one new object, private final object. Okay, log2, something like that. And then we can work here. We can also create another that is count2 static. Okay, that's fine, but we don't need static now. Now we can create here synchronized log2 and we can increase that. Okay, so basically, or maybe we can, it will be a very good thing if we create one new method, right? So here, get count. Okay, maybe we can see in this one, if any thread want to read this data, right, like this count, then that thread doesn't have to wait for this lock because that thread only need to acquire this lock. Okay, so we can write and we can also read concurrently, but then again we are using different locks, so we may get like stale data. To work with same state, we must use the same lock. Okay, so this one is not good practice. This one is for understanding. You should use here lock. Okay, instead of log2 for this. And for count2, we can see another like log2 practice that will be public void increment 2. Okay, and here we can get that. So that's fine. And now we can see this better counter, how we can run this one. Better counter this one. Okay, maybe we can see our normal syntax like that. We can create two threads. Okay, all right, that's fine. Now we can start. We can wait for them to complete or finish, and then we can call .get count and get count 2. Okay, and we can see one more like thread t3 that will be equals to this one. So o.increment. Okay, this time we will get like 20,000. Okay, accurate value. All right, that's fine. We can wait for that as well. We can start, or maybe we can put here join, and we can start that one here. Okay, now if we rerun this one, then you will see 20,000 and 10,000. Okay, so this is how we can work with our logs and also synchronized blocks with different logs. Okay, Now we can proceed further. Synchronized block is done. And also, if you want to see the actual implementation and how like JVM works with our synchronization blocks and methods, then basically that is complex. And also we don't have any inbuilt like that we can inspect in our object class, lock variable or kind of thing, because most of the time we don't need synchronization. Okay, so our JVM appends one hidden layout, we call that object header, to every single object automatically during memory allocation on our heap. Okay, and that header will contain something like mark word, and we use that one for synchronization. Now next thing, methods versus blocks. Synchronized method, synchronized blocks, locks entire method, locks only specific code, always locks on this or class, can lock on any object. Okay, we can create any particular object for that. And simpler syntax, more flexible, may hold lock longer than needed, minimizes lock duration, good for simple cases, for complex scenarios. Now next one, when to use blocks. You only need to protect part of the method. Okay, different blocks for different resources. You are calling methods that might block IO. Okay, we can say something like that here. Now next thing is reentrant locking. Our Java's intrinsic locks are reentrant, mean if one thread that already holds one lock can acquire it again without blocking. So this prevents self-deadlock. And why is that? So let's say we have example here, and our thread A, let's assume, is executing this one, right? So that thread A basically can automatically acquire or execute this method as well, because these both methods are synchronized and we need the same lock, right? So if thread A is already holding that lock, then that thread can also execute all methods those require the same lock. Okay, because if that does not allow, then that will be a self deadlock. Okay, without reentrant locks, calling inner from outer would deadlock because the thread would wait for a lock it already holds, right? So from outer we are calling inner, and to execute inner method we also need one lock. Okay, but that thread already holds that lock, so we don't need to wait. Okay, how it works: JVM tracks which thread holds the lock and a counter. Each synchronized entry increments the counter. Each exit decrements it. The lock is released when the counter reaches 0. So let's say thread A enters this one, and then we increased our counter to 1, right? Then thread A again enters this one, then we again increased counter to 2. Now after finishing this method, we decrease that counter to 1, and after exiting this one, we decrease that counter to 0. And for 0, that means we can free that lock. Okay. What synchronized guarantees? The synchronized keyword provides two crucial guarantees: mutual exclusion and memory visibility. We have discussed these two. Why does visibility matter? Okay, something like that. You can see each CPU core has its own cache. Thread A on core 1 writes data equals to 42. That value might only exist in core 1's cache. Thread B on core 2 still sees the old value. Okay. Without synchronization, there's no guarantee that one thread's write will ever be visible to another thread. Reorder instructions for optimization. Okay. Thread safety strategies. Making core thread safe isn't just about adding synchronized everywhere. There are several strategies. So first one, we have immutability. So if our object's state cannot change after construction, then it's inherently thread safe. So no synchronization needed. Thread confinement. Keep data confined to a single thread. If only one thread accesses the data, there's no race condition. Okay, so thread local, we'll see this one. Now next one, we have synchronization. Use locks to ensure only one thread accesses. Synchronized reentrant lock, we'll see this one in our next chapter. Then we have atomic operations. We'll see atomic like concurrent collections in our next chapter. So that's fine. Now common pitfalls: synchronizing on wrong object. Different instances have different locks. Synchronizing on this in two different objects provides no protection. Synchronizing on non-final fields. If the lock object can change, threads might synchronize on different objects. So if you do this one, then this lock can change, right? Change lock. Now threads use different locks. So make sure that you are using here final, like here we used, okay? Incomplete synchronization, over synchronization. Don't synchronize on string literals or boxed primitives. String literals are interned, okay, and shared across the JVM. Boxed primitives may be cached. Synchronizing on them can cause unrelated code to conflict. Okay, never do that one, because our Java uses string memory pool. So all code using this literal shares the lock. Now we have quick summary and we can move forward to our next chapter, which is advanced synchronization.